and degree higher than n. And anything else? What do I mean by that? I don't know. Degree 7 over degree 2. Degree 3 over degree 2. 3 over 2. These do not have horizontal asymptotes. Only these two have horizontal asymptotes. If the degrees are the same, which is not the case here, but assuming they were the same, then it would have been, assuming they're in descending order, it would have been 6 over 2. And I'll show you how. We find the limit in a minute. But if the degree is this 4, and here is bigger than 4, it's this situation. Higher degree in the denominator. Well, that is always the case. Either positive or negative infinity of f of x, the answer will always be 0. When the degree in the denominator is higher than the degree in the numerator. So let's say it's not clear. How do we show this? Very simple. Let's show it. So I'm trying to find the limit as x approaches infinity from 6x to the 4th plus 4x squared minus 7 divided by 2x to the 5th minus x plus 3. I know the numerator goes to infinity because the most powerful one dictates when x approaches infinity, the top goes to infinity. The most powerful in the denominator, when x approaches infinity, it's infinity. So this we really, really like because we have a method called L'Hopital's rule. So this is limit as x approaches infinity. I differentiate the top, 24x to the 3rd plus 8x. I differentiate the denominator, 10x to the 4th minus 1. Again, the same principle applies. The numerator goes to infinity, the denominator goes to infinity. I apply L'Hopital's rule again. So then the top will be that's 72x squared plus 8 over 40x to the 3rd. And you got the drift. I'll continue. It's infinity over infinity. The limit as x approaches infinity. What do I get? 144x divided by 120x squared. And I simplify. And when I plug in infinity, the numerator is 144. The denominator is infinity. So 144 over infinity is definitely 0, which means y equals 0 is a horizontal asymptote. And it doesn't matter if I do negative infinity or positive infinity, the answer is the same. So in short, for rational functions, horizontal asymptote exists only if they have the same degree. And how do I determine the horizontal asymptote if the degrees are the same? The leading coefficient over the leading coefficient. So in this case, if they were the same, the horizontal asymptote would have been 3, 6 over 2. If the degree in the denominator is more powerful than the numerator, only at infinity, the answer will be 0. But if you say, calculate the limit as x approaches 1, I'll have to plug it in. It's not 0. But if I go to infinity, x goes to infinity or negative infinity, this will overcome that, as you saw. 144 over 120 times x, but x approaches to infinity. X approaches infinity, goes to infinity. So that's why this is huge in comparison to 144. That's why the answer is 0. And if you have anything else, these do not have horizontal asymptotes. There is only one with slant asymptote, only one type, this one. When the numerator has a degree that is exactly by 1 unit higher than this. Why? Because the ratio has to be aligned. That's the slant asymptote. But here the ratio is not aligned because the numerator has degree 7, the denominator has degree 2. So the answer, the quotient will have degree 5. Degree 5 is not aligned. But degree 3 over 2 is aligned because the degree is 1.
How do we graph a vertical?
Say it again.
How do we graph one of the vertical asymptotes?
So as an example for vertical asymptotes, we have, let's say, f of x equals 1 over x minus 2. X equals 2 is a vertical asymptote.
Sorry, I meant a diagonal, like not a vertical or
Oh, so you're talking about slant?
Slant, yes. Sorry,
Okay,
I don't remember the name.
right. So for a slant asymptote, we have to divide. So here's an example. So a function like this, let's say x to the third plus 2x squared minus 4x plus 10 over x squared minus 1, this will have a slant asymptote. Because the degree at the top is 3, the denominator has degree 2, and the difference is exactly 1. So when I divide these two using long division, I will get a quotient to be a linear expression. That linear expression is the slant asymptote. So x to the third plus 2x squared minus 4x plus 10 divided by x squared minus 1. Remember, they have to be in descending order, both of them. Secondly, if there is a missing term, if this were missing, I would have had to leave a space. Descending order, and if this is missing, I have to leave a blank space because I have to use it, or I may have to use it. I don't know. Depends. So x squared times what is x cubed is x, and now I have to go back to both, distribute, change the sign, and write under like terms. So x times x squared is x cubed, but I change the sign because I subtract. And look now, this is negative x. I have to write plus x where it belongs, not here. This is gone. I bring down the next in line, and this is negative 3x. And that will be the final question. X squared times what is 2x squared? So it's plus 2. Again, 2x squared minus 2x squared, negative 2, but plus 2. And it has to be written under the like term. So then I have negative 3x plus 12. And I can no longer divide. I can't say x squared goes into negative 3x how many times. So then coming back to my function, then I have the quotient, which is x plus 2 plus the remainder, negative 3x plus 12 over the divisor. This and the quotient alone, this, why? Because this approaches 0. Lower degree at the top versus the denominator. So this will eventually go to 0. That's why this is the slant asymptote. So y equals x plus 2 is the slant asymptote. And how do I graph this? Very simple. When x is 0, y is 2, 0, 2. When y is 0, x is negative 2. So x equals negative 2 when y is 0. So negative 2, 0. So it's like graphing a line. So negative 2, 0, and 0, 2. So this is the slant asymptote. And at infinity, the function has to follow it. I don't know, from above or from below. I don't know, but it has to follow it. Same here. I don't know, from above or from below. That's the whole purpose. Right here, the function has to get closer and closer to this line. Here, the function has to get closer and closer to this line. I don't know how, from above or from below, just one or the other, not both, because otherwise it will not be a function by the vertical line test.
That makes sense. Thank you.
Thank you. Okay, next topic. Anything else? Have you looked at the previous test? Do you want to go back to any topics from the previous test from last week?
I was wondering if we could do on page 304, number 75.
75 on 304, of course. Okay, so find the slope of the line tangent to the graph of, okay, so we have f of x equals 2e to negative 3x at the point 0, comma 2. So they want us to find the slope of the line tangent to the graph at this point. Okay, so what do we need to do to find that slope? So we don't have to determine the equation, but I'm just saying y minus y1 equals the slope times x minus x1. So this is what they want. The slope of the tangent to the graph of this function at 0, 2. But we don't need to determine the equation. We're only asked to find the slope of this tangent line. How do we find this?
Do you have to find the derivative?
Of course, f prime of x is 2e to negative 3x times the inner function prime. Please make sure you put parentheses. So this is negative 6e to negative 3x. And all I have to do is just plug in 0 now. So this slope is f prime of 0. And when I plug in 0, this is 0. E to 0 is 1 times negative 6. So this is negative 6. So this number is negative 6. So any number raised to 0 is 1 except 0. That is one of the 7 indeterminate cases. 0 raised to 0 is one of the 7 indeterminate cases. We only looked in this class at 2 out of 7.
What is the second one?
What is what?
What was the second one?
0 over 0 and infinity over infinity. The two that we use that can be used with L'Hopital's rule.
Oh, okay.
So only 0 over 0 and infinity over infinity. And these are the only ones for L'Hopital's rule. The other 5, let me think for a second. Infinity minus infinity, 1 to infinity, 0 to 0, infinity to 0, 1, 2, 3, 4, 5, 6. I'm missing 1. 1 to infinity, 0 to 0, infinity.
Is it the one you just mentioned?
No, it's a product. 0 times infinity.
Oh, okay.
So 1, 2, 3, 4, 5, 6, 7. Do not assume that 0 times infinity is 0. No. It could be, but we don't know. So there are 3 products, 3 powers, 1 product, one difference, and 2 quotients. These are the most difficult to work with.
So the infinite power is indeterminate? That's interesting.
Yeah. Yeah. They are indeterminate cases. They can be anything, in other words. We cannot make a decision before we look at the problem from the beginning till the end. These are the most difficult. These are the easiest. This is and this is easy. It just requires an algebraic manipulation of the function. But these are the most difficult ones to work with, because we need to apply natural log in all those cases. Good, but this is not in your course, just these 2.
I have a question.
Ready.
On page 510, it's number 55.
Good. So we have di over dt, which is, I think that's h, k, and I. Am I correct? I is the investment. Okay, so I is I. H Yes. Is the investment productivity. So it's a constant. Okay, H is a constant. K is the marginal productivity to the consumer constant, and T is the time. Okay, so H and K are constants, I is the variable, and T is, okay. Use separation of variables to solve the differential equation. So that's our first step. Okay, so again, don't bother with these two because they are constants. So of course I have to bring I in the denominator, and I have dt. So first, if you want, you cross multiply. So di equals hki dt. And I has to go on this side, and I cannot just move it. I have to divide by it. So di over I equals h, k, and dt. At this point, I separated the variables so I can integrate. Remember, 1 over I is natural log of the absolute value of I. And on this side, this is a constant, goes in front, so hk, and the integral from 1 is just simply t plus a constant c. So at this point, we have to solve this equation. So there is the base here, which we don't write for natural log. So e to all this is the absolute value of I. So this is, if you remember, we broke it up into two pieces. So e to a plus b equals e to a times e to b. So it's going to be e to this piece multiplied by e to c. Now, I have to go back and take a look at the problem one more time, but if we're not given any initial conditions, please remember, and some of you forgot, and I wrote it in the solutions, this has to be plus or minus. E to c, e to h, k, t. Why I put this first? Because it's a constant. So now, this may change if they give us an initial condition, but this is the first step. So let's go back to the equation. Okay, now they are giving us an initial condition. Rewrite the solution in terms of the condition that I0 equals I of 0. So there, this is just a notation. I sub 0, I naught, if you want, is I of 0. Okay, so when I plug in 0 here, this disappears, it's 1. So then e to c, they are not telling us whether this is a positive number or not. So e to c will basically be this I0. So now the solution, again, they're not telling us, I have to read again, and maybe this is always positive. If this is always positive, then I have to choose positive. We'll go back and see in a moment. So then this piece is the I0. I0 with plus or minus e to h, k, t. So this should be it. But now let's go back and see if we can have plus or minus. So let me read that again. So, okay, so this is, I is the investment. Since we cannot have a negative investment, then I will say, I'll go back and say, this is correct algebraically, but only plus. Because I can't have a negative investment. Right? So then I equals I0 e to h, k, and t. And this is it.